Thank you all for coming. This is the last lightning talk and the last talk you will hear today about machine learning and graphs. My name is Shin, and I am a developer relations intern at Neo4j and have been for the past spring and summer. And I'm also in my last year as a student at UC Berkeley. And as I'm sure you've heard already today, machine learning is an exciting topic right now. Everyone from our customers to community developers want to make more informed decisions with the data that they have. And as part of the developer relations team, DevRel always loves to explore new topics that excite our community of developers. But the rest of my team is also really busy organizing events such as this one, providing user support, updating and maintaining the community site, writing super awesome blog posts, and so much more. So it's funny that this is the last talk about machine learning, because I think for my team, when it came to developing a foundation in statistics in order to analyze how machine learning best fits in with graphs, they might have had the thought, let's make the intern do it. And what I'm trying to say is that a lot of you here might know way more about machine learning than I do, in both theory and practice. And in fact, when I started working at Neo4j last February, I felt a little bit swept out to sea. And there's a lot going on here. I won't go into it in too much detail. But since then, I've learned a lot, and now my work is a bit more peaceful. I have my own little boat and a guiding question. And basically, I'm not pretending to be an expert. I've just been given some time to teach myself about machine learning and to consider this question: where does machine learning fit in with Neo4j? And I'm here to talk about sort of a unique space, which is machine learning and graphs, and even more specifically, machine learning as implemented as procedures in Cypher, similar to the graph algorithms library. But I don't want to get too far into a hot topic like machine learning without defining it a little bit. So to start off, what is machine learning? And basically, it's just, as far as I've been working with it, an application of statistics so that machines can learn with data. And this is scary to some people who think that someday machines will get too powerful. But don't worry, it's all just data cleansing and a lot of math. And specifically, machine learning algorithms, such as neural networks and deep learning, are really just a computationally exhausting amount of calculus that allows machines to do what humans do easily, much less well, but at a greater scale. And so let's start off with a little bit of human learning. And this is from the classic iris classification data set. And I had never, before making this slide, actually took a minute to think, what, as a human, would I do to classify this fourth image? So can anyone predict which class versicolor setosa or virginica the fourth flower belongs to? Don't worry, I started panicking at first because I thought they all looked the same. But then I looked at enough Google images of iris flowers that they started actually looking different to me. Setosa, right. Good job. So, so when it comes to asking the question, how can we train a machine to do this for us? We really need to start thinking about what quantitative differences in the flowers allowed us to classify the last image so quickly. And so the iris flower has two main features, which is the petal and sepal. So in this case, we want to identify each flower with 4 quantitative measurements, which is the 4 listed here. And since this is a classification problem, logistic regression is the model that we want to use. And logistic regression assigns a weight to each known variable using known data points. And the logistic function f just takes the weighted combination of these values and maps it into as a value in between 0 and 1, so that the output of the logistic function can just be interpreted as a probability that a given flower belongs to that class. And so for each known data point, you can think about the model taking little steps towards better and better predictions. And in the case of the iris flowers, you would create 3 models, 1 for each class. And once you have your models trained, you would input an unknown flowers data into all 3 models. And then you would say that the class that that flower belongs to is the model with the highest output probability. So this takes us back to the question, how does machine learning fit in with graphs? And before I started working at Neo4j, most of the actual incorporations of machine learning and graphs that we had produced were just integrations with existing software. So in order to use these, you would export graph data into another software, run your analysis, and then take the model parameters that you created and then import them back into the graph. And this was great as it helped existing customers that might be asking questions about how to do this exact process. But since data is exported and brought back into the graph, it doesn't really take full advantage of the fact that when you use a graph database, your idea is you want it to store your data. And ideally, it would be able to store your data while you're performing machine learning analysis. And this is the approach that a lot of industries use when they're using machine learning and data science to solve their problems. They would dump their data from the day and analyze overnight, and then bring those decisions back into production the next day. And this past spring and summer, my work was to extend our query language Cypher with user-defined procedures so that from the Neo4j browser, you can train models while the data, instead of using this approach, the data could remain in your graph. And I extended Cypher, as I said, through user-defined procedures. And these are written in Java and then just deployed to Neo4j as plugins. And then after this, they're accessible from Cypher, just like the graph algorithms library. And in this case, the models that you would create using these procedures would be stored just in the static maps of the Java classes. So let's go back to our flowers. In fact, iris flowers produce in 2 ways, either through asexual reproduction or through the hybridization of 2 flowers. So let's suppose that we have an iris flower breeding program. And then we input our flower data into the graph as mother and father relationships. But for some flowers, we don't know which of the 3 classes they belong to. We're given the 4 measurements from before, and we want to keep our data in the graph and run user-defined procedures to create a logistic regression model. So using the user-defined procedures that I created would look something like this. And this is just a Cypher screen capture from the Neo4j browser, but you could also run these through like a Py2Neo script, as long as you're using Cypher to interact with the database. So when we create our model, we just need to give it a name, specify the 3 classes that the flower could belong to, and then specify which features we're going to use to classify our flowers. And in this case, you need to say that those features are numeric by saying they're going to be in double form. And next, you query to find all iris flowers with known species. And then we add them to our model just by specifying which model we want to add them to. What are the 4 feature names and values stored in the iris nodes? And then what is the correct classification? And then finally, to predict, you can query for all flowers which don't have a known species. Say which model you want to use to predict the species, give the known feature values, and then the predicted species will be stored in the node. So this approach differs from previous approaches by eliminating the data export step. And graph databases store data, as I said, and so ideally they should be able to hold data while we build models. And these procedures that I wrote only deal with one data point at a time, so there's no memory burden, and they can be updated just as dynamically as the graph. But I'm unsure how this is maybe one of the most simplistic machine learning algorithms, and it's still to be explored how this approach would work for more complex algorithms. And when thinking about how we can improve our approach, we go back to the question, where does machine learning fit in Neo4j? Were these procedures that I created the best use of graph databases in machine learning? How can graphs set Neo4j and the machine apart in the how can graphs set Neo4j apart in the machine learning space? And this is maybe the easiest and most straightforward approach, is just that the same performance benefits that you get for running your standard queries by running them on data in a graph database, you can get those same performance benefits when you're trying to collect feature values to be input into a machine learning model. And for example, if you wanted to find a user's number of friends and use it to predict some other information about that user, you could just query a constant time to find how many outgoing nodes relationships are going out from that user node. Whereas if you were using a relational system, that might take costly joins. So this would assist you in any sort of approach to machine learning with graphs, is just the speed up in building your training data set. A bit more complex is using graph structures to restrict the potential relevant data points. So for example, if you had a deduplication need where you have user fields from 2 different products and you wanted to find which users corresponded as the same user, then if you were to make all possible comparisons, that would be a Cartesian product, which is very, very costly. But if you were to have your data stored in a graph and then infer groups of similar users using the graph structure, then that could restrict your comparisons and make your runtime feasible. Another approach to using the graph structure is to actually bring model development into graph. It's hard to look at all of the machine learning algorithms and see that they're represented in graphs as graphs logically, and to not want to bring those in as graphs into Neo4j. For example, a neural network, you could represent each neuron as a node in Neo4j, and this could also help us better understand the neural networks that make such great predictions. Model transparency is a big problem in deep learning today, just because these models assign weights to every edge between the neurons, but humans can't always understand logically why these weights lead to successful predictions. And then another issue with this is that there is a lot of computation required in maintaining and training neural networks, and I'm not sure how that computation would work if the network was represented as nodes in the graph. There would definitely need to be some optimizations made. And then another interesting approach related to this is model version control. Version control of machine learning models is definitely a graph problem, because as you're developing the models, you don't just immediately know what to do. You have several different versions of models that develop from each other, and also slightly altered data sets. So representing those relationships in the graph would make for a really interesting graph problem and help a lot increase the transparency in the process for building machine learning models. And finally, this is an area that most excites me, because when I think about machine learning and graphs, I think, how can graphs allow us to make insights that we otherwise wouldn't be able to? Like, where is the benefit? And there are, in research fields, a lot of new machine learning algorithms that rely on graph-based input instead of vectors. And for example, the graph edit distance would be a similarity algorithm that takes graphs, that quantifies the similarity between subgraphs, so that if your input data is in the form of a graph, then you don't need to flatten your graph data into a vector. And as we all know, because we're here today, a lot of times graphs have are a way better way to express our data. So why should we have to extract that underlying graph, or remove the underlying graph structure when we take that data and put it into a machine learning model? So thank you for listening. And all of these are very much in development. And sometimes the coolest implementation is not always going to be the most practical. And if you would like to see more how the procedures that I wrote can be used on an actual data set, you all, if you're signed up for training, should come to the machine learning training tomorrow. We're going to walk through a lot of it. Does anyone have any questions? Yeah?
What's a machine requirement for tomorrow's training program? What should be on your laptop?
For, what was that?
Training program. What should be on your laptop?
Oh, so it's just a plugin. It's online on my GitHub, and I wrote a blog post called Graphs in ML, Multiple Linear Regression. That's on our Medium publication. So yeah, you just have to download the jar file and just stick it into your plugins. And then also, you just have to go into your database's settings, and where it says the procedures.unrestricted, just add that to the allowed procedures. Yeah. And there's documentation online in the README about how to best call the procedures and what sort of form the input data should be in. Yeah?
Any other algorithms available right now? Other
Just linear regression in a single and multiple variables. Yeah.
In the context of like the relationships, like is there a way to kind of like hide them or like turn them off like temporarily? I know like certain like neural nets and things like that, they'll have different ways that they kind of like eliminate bias by like turning things on or off in terms of like neurons firing and stuff. Can you do that with Neo4j? Like can you like turn a relationship off temporarily and then bring it back later?
I am not sure.
What you can do with Neo4j's graph algorithm in general is direct the graph to a subgraph basically, and that could include kind of leaving off relationship or weighting relationship types differently.
Okay,
So you can have kind of full control usually about like what the shape of the graph is you want to run the algorithm. So that's what we also support for the deep work and deep GL implementations. For the linear regression, it's not so important because you pass it directly the values that you want to train on. So it's up to you where you pull them from. So it's fully controlled.
okay.